as angstroms and so forth, and the spacing between each of these atoms, each of the points here is going to be in angstrom scale. Therefore, the light that we need to use here is on the X-ray radiation angstrom sort of level as well, so that when we actually shine our light in here, then we're actually getting this type of constructive and destructive interference of our different wave-like properties going through in here. Okay, so that's why we're using X-rays. Okay, our crystal is of the same size, commensurate size as the crystal structure itself. Okay, good. So here, for example, we're looking at waves of the system. We're using waves as our X-ray. Is this an elastic or an inelastic experiment?
Inelastic, because they are rigid.
Because of what's right?
Inelastic.
Why is that?
Because the cells or the crystals, they are fixed at their positions.
So if you think about it, what's an elastic process?
I think something that changes but then comes back to the initial position.
Yeah.
Or initial.
Yeah. So elastic band. Sorry, jump off. Elastic band. Yeah. So we'll go back to its original place. If it was inelastic, what would happen?
It just wouldn't change. It wouldn't move. So I guess here this scattering would be inelastic because you won't change the position, say, of the atoms or molecules or their valency or charge.
So yeah, so an elastic process, for example, is one. So elastic is where you put energy into a system and the energy you get out is the same. Okay, so no matter what happens, this energy in is equal to the energy out. An inelastic process is where your energy in is different, or sorry, the energy out is different to that going in. Okay, so it's either you may have gained a little bit of energy, or you lose a little bit of energy depending on what you're doing. Okay, so for example, we can take a brief detour into Raman spectroscopy, for example, because we use that also. Okay, so what essentially happens in Raman spectroscopy, we've got our energy levels, so we've got our ground state here, and what I'm going to call this is a virtual state, virtual energy state. This isn't an excited state, by the way. Okay, for Raman, it is just a virtual state. So normally in Raman, in an absorption process, we might, an absorption process, this would be IR, where we're basically putting in IR radiation. That IR radiation is the right wavelength, right energy to promote it up into a slightly more higher vibrational energy level. Okay, so you can remember that each of these levels here it represents a sort of a vibration, as it were, in your system. So you put enough energy in that atoms will start to vibrate and move. Okay. And the process of IR is the IR energy, that light going in, is sufficient to be able to start letting something vibrate. And we get to see that if there's a change in dipole moment. Okay. Raman, however, is slightly different in the sense that you are providing a huge input of energy through your laser. Okay, so you'll get it up into this, what I deem as a virtual energy state. Okay, this is sort of like a combination of a molecule with light. Okay, so it's a movable object, and we can go into Raman at a later date. But essentially what we're doing is we're putting in some energy here, and then we're letting the molecule relax, or the energy to relax back down. Okay, but it may be a case that you've put in this much energy 1, and then you get energy 2 out. Okay, and by this process here, you've input the energy. Some of the energy has been given to actually move the molecules themselves, or atoms, and therefore the energy that you're getting out at the end of the day is slightly reduced, because that energy has been used for kinetic surface. Okay, so this would be deemed as an inelastic process, and that is what's termed as Stokes shift. Okay, and that's what you're seeing in everyday ramming. If you've got ramming, it's the Stokes shift that you're looking at in general. Okay, so that's you kind of where E1 is greater than E2. Okay, and that's the Stokes. Okay, you could have a process by which you are in a higher energy level. Okay, so you're starting off at a slightly higher vibrational energy level. So, for example, a molecule at high temperature, you've increased the vibrations and moving around, so they're slightly higher in their thermal energy has been given to them, so they're slightly higher, and you may get in the more energy out. Okay, so you might find that E2 is greater than E1, and that is what is deemed anti-Stokes, anti-Stokes. Okay, and that is a very weak process. Okay, that's far weaker than the Stokes process. Okay, so kind of going back to the topic, what we're doing here with X-rays is we're putting energy in, which is the X-rays. Let's forget about absorption processes within crystals and so forth. We are getting energy out at the same wavelength of light. Okay, so we've got an elastic process in our system that we're looking at. Okay, is that clear so far? Yes.
Yes.
Yeah. Then, as you happy? Yeah. Okay. Good. Okay. So the question then is. How do we use all this information then to try and get through to the diffraction? So let's think about why does something diffract? Why does a crystalline solid diffract in an amorphous form? Doesn't it?
Bragg's law.
Bragg's law, okay, but before that even, what just fundamentally about the solid?
Long range order.
Yeah, okay, so you've got long range order associated with your system, okay, that's good. So what we've got is and how's that? Right, yes, okay, so we've got long range order in our system, and that gives rise to Bragg's law in our system. Now, we have Bragg's law, we're shining our light on the system and we're getting the construct of interference based on that thing, so we'll need to come round to Bragg's law. Let's go and have a look at that. And I'm now going to have to turn my book. Don't get sick, everybody. Don't get sick.
Just try some little visualization that might help in the coming minutes.
Right. Okay, so here is, what is Bragg's law? It's on the diagram. What is Bragg's law? Bananas, what is Bragg's law?
Like the equation?
Yeah.
The wavelength equals 2D spacing and sine 2 over theta.
Sine theta. Okay, so we've got n lambda, so it is your n lambda. Okay, is 2d sine theta, right? So how is that constructed then? Okay, so here, for example, is the method of construction that we can have a look at, and thanks for that. This is the construction here, and so what we're ending up having is that in our crystal, whatever, what we're wanting to do is scatter off our atoms, for example, and this is a very simple way of looking at this. So, for example, we've got our two incoming rays here, and they're going to interact with an atom or whatever, and then it's going to go off as outgoing rays here. Okay, so the way in which, so for us to be able to see the spot, what has to happen with this light coming in and this light coming in here? What needs to happen? Remember, let's just think of them as separate waves. Okay, we could think of them just as a incoming in like this. I'll need to get this. Okay. I'm trying to do my best to measure. There we go. So we've got our two waves that are meant to be commensurate with one another and going in a positive direction and constructively together. So what do we need to think about that? How do we get our outgoing waves to do the same thing? Does it matter what the spacing is between these two things here, or is it for us to be able to see here, what do the waves need to do?
They need to interfere at a specific angle, and then there must be also the d spacing has to be equal to. Is it like the distance between like the peak and the clock?
Yeah. Okay. So Okay. So what we've got here then is, if we take this first one here, it's going to interact there, and then it's going to go off and be scattered in this direction here, and that's fine. We don't need to worry about that individually. Okay. So as soon as it interacts with, so it actually comes in. If it interacts with it, so it'll be interacting with what in the atoms. What do X-rays interact with?
The electrons.
So the electrons. Okay. So we've got our interaction of our X-rays with our electrons. In that interaction, is the wavelength the same? Is the wavelength will be the same because it's the same energy, therefore the wavelength will be the same. But is the phase going to just continue on in the same way, or is there any what happens to our wave? Pardon?
So I was going to say, well, it's scattered, but then it's only picked up when it's then in the same phase as the. Hard to describe.
Okay, so yeah, go for it, Julia.
So they have to be the same phase so that it doesn't cancel out.
Okay, so wavelength is going to be the same. But what's going to happen is that as soon as any radiation hits the electron cloud, its phase shifted by 180 degrees. Okay, it's every single interaction like that is happening at the same time. So everything just gets shifted by 180 degrees. Okay, because everything is doing it, it doesn't really matter, and we don't need to worry about it. Okay, if some of them did and some of them didn't, then we need to worry about it, because all the waves undergo this 180 degree shift in the wavelength in the phase. Sorry, then we're going to don't have to worry about it because everything does it. So what do I mean by that? What do I mean by that? Okay, so what if say we're going in and we've got our wavelength like this, and it stops. Okay, this is our interaction. Let's just say it's our interaction with our electrons there. Okay, what we're wanting to do is we're going to have a 180 degree shift in that. Okay, so remember you've got 360 degrees over a wavelength. Okay, so from here to here. Okay, that's our wavelength. Is our wavelength. Okay, but what we're going to do as soon as we interact with the electrons, what's going to happen is that we're going to have a 180 degree shift. Okay, and the thing is going to do this. Okay, so instead of being at the peak, you're now going to be at the trough and starting to drop, and so forth. Okay, does that make sense?
Yes.
Okay, it doesn't need to. You don't need to worry about it too much. Nobody will ask you, but it's just something to bear in mind. And because it goes across the data set, it doesn't matter. It happens with all atoms. Okay, so that's what's happening to, say, for this incoming ray and going out again. Okay, I haven't necessarily drawn this, but I should do that. Okay, so that, let's just say that's the continuous incoming ray, and we've got no problems about that at all. The problem arises when we try and couple it to this ray here, or couple this ray with this. Okay, we want to have constructive interference here. Okay, so we want to make sure that this bottom wave here and this bottom wave here and this top wave here, they need to be in the same phase. So I'm wanting to ensure that it is going to go off like this. Yeah, that's what I want to ensure. So I've got my wave going in like this, and they're all happy to about here. But then something we need to worry about is we need to worry about this extra distance that is part of that equation. Okay, so because these lines are parallel with one another, this bottom wave actually travels just a little bit further, and then on the incoming, and then it needs to travel that little bit further on the outgoing. Okay, do you see that? So the thick lines there and there. Okay, so this is chapter 5 of Durham School. Okay, now because there's that extra little bit of travel, and we know, because we want the constructive interference, we know that these two bits here, they have to be a length, a wavelength. It has to be some sort of wavelength. It could be one wavelength, 1 lambda, it could be 2 lambda, 3 lambda, 4 lambda. It doesn't really matter. It has to be a total length of a wavelength. It can't be partial, it can't be 180 degrees or anything like that. So those things have to be n lambda, we'll just call it. Okay, so that's us essentially in our equation. We're saying that this has to happen. Okay, the n lambda has to happen. Now, what we then need to think about is, okay, how do we construct this then? How are we going to come round to understand, get to the Bragg equation, which is 2d sine theta? Now, if you imagine we have got this extra distance here, how do we do that? Well, through trigonometry. What we're able to do is we're able then to find out what the extra length here at the bottom is going to be. Now, we're diffracting at a certain angle, so the alpha angle out here. Now, by doing that, what essentially that means is we've got an alpha angle here, this is going to be 90 degrees in here, and therefore this is going to be your alpha here, in this small region here, and therefore what we've got is our adjacent, sorry, where is it? No, sorry, it's that. I've got this wrong, sorry. It's this one here. Idiot. Okay, so you've got your alpha in there. So you've got your adjacent length here, which we want to find out. And we've got our hypotenuse here, which is our d spacing between our materials. Okay, so the distance between these atoms here are d. Okay, so we've got our adjacent and we've got d, and therefore we can say that this length here is a cos alpha. Okay, and this distance here is just going to be a cos alpha, and have the 180 degrees minus this angle here, because it's 180 degrees, and we're getting to know what that angle in here is here. Okay, and so because we've got because we know what these angles here and this angle here, the addition of a cos alpha and the minus a cos alpha 0, what we can actually equate that to then is just by using trigonometry and trigonometric equations, we can start to say that this length here is 2d sine theta. Okay, so this angle here, no, these two lengths, sorry, here should be 2d sine theta in the length. So essentially, if we don't have that relationship between these lengths here equaling an integer value of our wavelength, then these two waves here, outgoing waves, will just not work properly. Okay, and they will be destructively interfering, and therefore you won't have the correct thing, the correct relationship. Okay. Right. So we've got so that's the sort of relationship we've got here. So in general, the n here can just be forgotten about, because we can always just say, oh well, it's 2, 3, 4, and we can always choose a different set of planes. So if we for example, instead of having the 100 set of planes here, for example, we could have the 200, 300, 400, 50, and the relationship still happens. Okay, so it doesn't really matter that. So that's why sometimes you see it just written as lambda equals 2d sine theta, but actually it should be n lambda is equal to 2d sine theta. Okay, so what would happen, say, if we were in the same position, but that d was like fractionally out? What would happen should I just change that by a nanometer?
Your length would change and then the rule wouldn't apply.
Pardon, sorry?
So if the d spacing changed, then the extra distance that it has to travel would also be impacted. So then this relation wouldn't apply.
Yeah. Okay, so it's incredibly severe. Okay, so the Bragg equation and the rules governing this are incredibly severe. So if you are ever so slightly off in this, then it's just not going to happen whatsoever. And so it's a really very important law, and it's that needs to be, the conditions need to be met for it to actually happen. There was a Royal Society lecture which you can try and remind me of. I will try and remember to go and have a look. But there's a Royal Society lecture where a guy, I remember, I'll need to see this, but he basically did the calculation for us. And he said, well, if you just change it by 0.01, it just doesn't hold, and it cuts off, and it's like that one. You can do it because I guess conditions. Okay, good. Okay, so that's the Bragg equation. Is everybody happy? Benaz, are you happy?
Yeah.
Sadia, are you happy?
Yes.
Yeah. Okay, good. So that's the rules that govern diffraction, and for this to happen here, then we're looking at long-range order. So obviously we're only looking at one set of dots here, but if you can imagine getting a million more, the crystal will build up. Now, what inevitably happens with so what happens if you only get a few points here? What happens to? Does anybody remember what the diagrams look like if you've got only 1 or 2 points here versus an infinite set?
So is it the bigger the set, say like the less clear the overall diffraction pattern that you get?
Yeah. Okay, so if you only take a few instances of this, okay, if you only take say a handful of dots in a row, then the interference that pattern that you're going to get is going to be quite blurred. Okay, it's not quite as sharp. It's really quite a blurry picture. Now, if you then increase that up to an infinite set or a crystal set, then what happens is those peaks, that pattern becomes really very, very sharp. Okay. Now, what consequence does that mean practically for us? If you're taking data on something, I mean, not everyone's doing pressure, but maybe under different stress conditions or anything like that. How does that sort of manifest itself in what we do in the?
You can see if you get, for example, powder pattern broadening in the peaks,
Yeah.
or
or then if you do single crystal diffraction, it's less clear really where so your reflections are sort of lying really close to one another but not in the same place, so then it's quite difficult to refine solid structure.
Yeah, okay, so you can equate this to being, to having going from a very highly crystalline sample to being something that's not. So we could, for example,
oops, sorry folks, I'm just trying to break everything. Oh my goodness me, I can tell I don't use this video.
This was actually bought for the Durham School. You don't work? Come on then. Sir? You don't work? Oh, that's because I switched the camera off. That's... There we go. Okay, so you can imagine that you go from a kind of a blurry picture like this for only, say, 5 atoms in a row to something that's really infinitely sharp when we've got lots and lots of dots in a row like this. Now what that equates to then is if you think about each of your particles within a single crystal, you've got a large infinite set of things here. As you go towards a powder, then you might start to fragment that. If it's a good powder, then you're still got lots and lots in a row, but as that powder deteriorates and becomes worse and worse, you're then sort of tending towards a situation like this, where you've got a lot fewer repeating units within each of those crystalline diffracting materials. There's not so much all in a row in order, and therefore you're going to start to get this kind of broadening of your peaks, just because you've got less unit cells in your diffracting part as you mill it, or if you go to higher pressures or whatever it might be. Okay, so just because something is single crystal or powder, it doesn't necessarily mean it is less, less diffraction or less crystalline. It does depend on what the kind of peak shapes are. All polycrystalline versus single crystal is whether you're actually able to see individual peaks in the diffraction pattern, and you're able to actually analyze a small enough particle to get those single crystal peaks. Each of those, given a smaller and smaller source, you could get smaller and smaller crystals. Okay, and in fact, if you think about the electron diffraction sphere, they've got a tiny beam, and they're looking at powder, what we would deem powder, but it's still mega sharp. It's still diffracting really well because there are enough unit cells there to be able to create this long range order and so forth. We're not got to a situation where we're like this. So really, the question is when does amorphous become amorphous? Okay, that's a query. I think somebody gave a presentation one, it's like 10 unit cells or below. That's when it becomes that you've done calculations and so forth. So it's that is up for debate. So not going to go there. Okay, good. So we've done our diffraction then. What else are we going to do then? Any other questions? Any questions at the moment? No?
So it might be unrelated, but so when you talk about the phase problem, was that to do with the wavelength phases? I know it comes later on, but I can't quite remember what the phrase.
Right. Okay. So yeah, it's right to point that out. Okay. So at the moment, what we want to do is that we need to sort of separate out what that long range order is and then what the contents are, essentially. So for us to have Bragg diffraction, we need to have a spacing of our unit cells. We need to have long range order of those systems. So it has to be have that ordering associated with it. And if the solid itself has an order to it, it will likely have a diffraction pattern that we can then go and analyse. Now, I'm not going to go into quasi-crystals and all that nonsense, but let's say a crystal doesn't necessarily need to have long-range order, but let's just not go there, okay? For us, it does have to have long-range order. Then the question is, okay, what impact then does the phase problem have on the system? So we can measure a diffraction pattern of a crystal sample, that's no problem whatsoever, okay? The question, what we then need to think about is, well, what does that diffraction pattern tell us? And how do we know where the atoms are? So the question back to you is, how do you know where the atoms are? So you know what the size of the box, so in our lattice, our reciprocal lattice, our diffraction lattice, we've got an idea of what the unit cell information is. That's what we do, we collect that. So we're from this arrangement here, we're getting a set of lattice points, and we're able to see what the unit cell looks like. Okay, how do we get to the atoms?
So if you assign what electron density sort of region relates to each atom, but I guess it gets complicated when all the atoms are quite similar. So if you look at the top row, like organic molecules, carbon, nitrogen, oxygen, they're not that different, so it gets difficult to do that.
So what we can do is, if we go back to this here, okay, so Sadia, don't poke and don't cry. Others, you've seen this before.
Okay.
Okay, so these are the equations that are essentially that we've got to play with. Okay, so we've already talked a little bit about the Bragg equation here. Okay, that's we've seen what the construction of that is. So is that a viable question, for example, for those doing PhDs? Yes, quite possibly. Okay, can you derive the Bragg equation? How else can you derive the Bragg equation? I can maybe go into it in a different time. We can derive it from another means.
Could you look
Remember,
at
it's got somebody who's got a name not dissimilar to mine, but slightly different. Right, okay, so what I'm going to do is stop that, and stop that, and we're going to post into the chat. Okay, this was a piece of educational whatever videos that enables us to think about the eval sphere. Okay, and I will let you just go and have a look at that. I don't. Any advert that may pop up is not my responsibility. So it's a video of what the eval's construction is. Okay, essentially, by using that eval construction, you're able to see and derive that Bragg equation. Okay, so just be mindful that the one that we just did there is rather a simple way of doing it. The eval construction is just slightly different, but essentially we're doing it a different way. We can go on to that. We can do it at a different time. Okay. Anyway, that's an aside. So that's a YouTube video that you can have a butcher's at. So essentially what we're wanting to think about then is that we are wanting to think about what our electron density is. That's what we're really wanting to get at. Okay, so for every single scattered intensity, okay, here, what we're starting to see a scattered intensity HKL, so that's our measured intensity that we've got, okay? What that is composed of is some sort of information. It's a continuous function, okay, so an integral. Okay, so remember that integration is just kind of infinitely small additions across the unit cell. Okay, so that's what our integration means. It's just add. add up all the electron density over that every single place, so x, y, z, so anywhere in the unit cell, we're just adding up what the electron density is here. And then here we've got some sort of idea as to the size of the cell, the volume of it. But what essentially we're doing is we're summing up all the electron density in order for us to see all that sort of stuff, okay, which is fine. If we know where all the electron density is, if we know all this sort of stuff, and we can do the addition and the integration, then we're able to get back to, we can find out what the intensity is, okay? But that's not what the experiment is. Our experiment is knowing what this is, and we have to get to understanding where the electron density is, okay? So you can also write it in terms of looking at, so this is the same equation, but instead of looking at in terms of electron density, what we are going to do is we're going to actually put a model in place. Okay, and we're going to say, well, this model has spherical atoms, or it's maybe got anisotropic atoms. They are located at specific points, and therefore it goes from being just an addition right the way across the unit cell, or integration right across the unit cell, to actually having the sum of, so we're still doing an addition of all the different types of atoms given some sort of thermal parameter, okay, how much it wiggles and wobbles, and then it's the same sort of equation at the back end here, so 2 pi I based on HKL XYZ. Okay, so that's the position of the position of the atom, and the HKL is related to what the HKL value is that we've got in our diffraction pattern. Okay, so that's our spot. This is the XYZ relating to that spot, and we're just going to add up all the atoms in that system. Okay, so what you're seeing here is essentially for every single diffracted spot, all your atoms are contributing to all of your diffraction pattern in all the spots. Okay, so all atoms are contributing to each and every single reflection. So whether that's the 1, 0, 0, 2, 0, 0, 3, 0, 0, 4, whatever it might be, all your atoms are contributing to that, right? So if we do know this, again, similar to this, if we know where the atoms are, then we can get to this. The problem is that we don't. Okay, so what we're trying to find out is we're trying to find out what the electron density is. Okay, and this is the equation. This is the equation of that. Okay, now again, it's just going to be over all of sum over all of the HKL values. So there is the magnitude. Okay, so that's just the intensity of your whatever it is, your scattering factor, or your not scattering factor, your reflection. But then in here, for example, is the scattering, is the phase relationship, okay? And this pi part here, and it's that phase relationship that we just don't know what is happening to that atom. So we're going to be summing over the actual magnitude of the scattered wave, but then we need to understand how each of those then interacts with one another. Each of those scattered waves of a particular magnitude, but we don't know what the relationship between each of those scattered waves are. Okay, so overall, in our diffraction pattern, because we've got a crystalline substance, it is showing constructive interference to give us those spots. But then within those spots themselves, they will vary in intensity, okay, depending on where the XYZ is, okay, and their relationship to the HKL, remember, it's a portion, a slice through the unit cell. But what we don't know is we don't know what that phase difference between each of those scattered waves is. Okay, and that's where the difference is. And that's where you need to kind of separate out the concept of, yes, we're getting constructive interference to have Bragg's law because the orientation of the crystals in the right diffracting place. But then you've got the relationship of each of those scattered waves and those sine waves. Remember, each atom is going to be giving off those sine waves, but the relationship between those waves is just going to be ill-defined because we don't know what it is. Okay, so if you know where each of the atoms is, so if we know this, if we know where the X, Y, Z is, if we know that of an atom, then for a particular reflection HKL, then we'll be able to say, well, that's what it is. It's a nitrogen, it's a sulfur, it's a whatever. It's placed at this point in time, and therefore it'll be this distance from this particular set of planes, and therefore I know that that's going to be working, and therefore I can go back to my diffraction pattern. So I know what my crystal structure is, and therefore I can get back to my diffraction pattern. But having a diffraction pattern, I cannot get back to the electron density because of this stupid thing, this phi. Does that make sense? Or not? It doesn't. Please say if it doesn't.
If, like, I understand why if you go then backwards, it doesn't work.
Right, so one thing we need to think about, okay, so let's just go back and have a point. So say for example, if we've got our unit cell like this, okay, all that we're going to do is for every, for a particular set of reflections, so what do we do when we're indexing our sample?
So we are looking at where the reflections are, and then I guess the distance between them. And through that, we can tell what the unit cell is. If we know also the wavelength of the diffractometer, or the radiation, sorry.
Yeah, okay, so so you've collected a diffraction pattern, okay, and when you click on index, or so first of all you harvest those reflections. We've got a set of reflections. What do they make up then? What do we use? Bananas, what do we use to help us? We could press go on a computer, it'll tell us, but how do we help it if the computer's finding it difficult to index? What do we do?
Browsing letters.
So we've harvested all our reflections, you've tried to press index and it's just come out with nonsense. What do we do?
View the reciprocal lattice and remove the reflections.
Okay, so we're looking at the reciprocal lattice then, so we've got those reflections, so that's a three-dimensional plot of your diffraction pattern, isn't it? Okay, and then rightly so, we've got a centre. We know, because we plotted it up in 3 dimensions, we know where the centre of the diffractometer is, and then we know what relationship each of those spots has to the centre, okay? And as you said, Julia, you've got those distances. What we're looking for is those repeating distances in all three directions. What is a common distance? So one of them is, one way in which we do it is that you see how often a length comes up, okay? So if 3.2 in reciprocal, 1 over 3.2 comes up lots, then it will say, yes, this is a length. Similar with 0.84, it will be a length and so forth, and it will do that. Now, because we know what 0, 0, 0 is where the centre of the diffractometer is, what does that enable us to do? What are we able to do to our reflections?
Well, equate the reflections to particular lattice planes.
Yeah. Okay, so we're going to index. So by indexing, you're giving it a Miller index. Okay, so we're able, because we know where the center is, we can go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in X, Y, and Z. Right? We can count along. We can go 1, 2, 3, 4, 5. Okay, so I'm going to go and just where is it? Share. Let's just do that. Okay, so here is one of the NASA's crystals, for example, and this is our reciprocal lattice for our system. I've tidied it up. We had a whole load of nonsense involved with this. You can see how lovely the rings from different sources are and so forth. And then what I've done is I've gone and pressed in, I've tidied it up. How have I tidied it up? I've gone lattice plane, selecting those lattice planes like this, for example. And then I'm left with this diffraction pattern here. Now, if I hadn't indexed this, for example, it would not come up with anything. So what I'm going to do is I'm going to go back and I'm going to delete all of those. Okay. Now, because I have deleted all of this, you can see that the unit cell parameter is no longer available to us. Okay, we can't see anything, there's no box or anything to the unit cell there. Okay. I could, for example, measure and try and do this myself. Okay, I'll measure this out. It's 6.6, and then this one is, oh cricky, this one here, 24. Okay, and then move to the side, and then I can go and measure again. Measure. Okay, so I know that's about 19. I can do all that nonsense myself, but I'm not going to. What I want to do is I want to go back and determine the unit cell. By indexing that, that's what I'm doing. I'm using those reflections there to come to some sort of unit cell parameters that we have. Okay, so we've got our unit cell. There are however many, 800 and odd, that are conforming to that unit cell. And now that we've seen the reciprocal lattice, we're able to hopefully see the unit cell applied to the box here. Right. Okay, so we can actually see that reflection there. Now, if I zoom in then, and hopefully the dataset will allow me to do so. Okay, so you can see up in the corner here, that's going to be our 0, 0, 0, because that's where all our vectors are. What are they called? Thingy vectors?
Burgess. 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 Right?
Well, unit cell vector there. Okay, so what we've got here is a 0, 0, 0. We can assign that one to be 1, okay, along C. So if this is the C direction, this should be flagging up as 2. Now, in the original version of this, it used to tell you. But it looks as though it might not be doing anything. That's very annoying. No? Oh, that's a bit annoying. Oh. Should have probably thought about this before doing this. Settings, yeah. Miscellaneous. Show HUD labels. Oh, a bit disappointing. Shout to see it. And you need to know what that means or something. Oh, that is so disappointing. Anyway. What was that? Alright. What, do that? No? Oh, anyway. Doesn't matter. What we've got here is 1, and then it'll be 2, 3, 4, 5, 6, 7, 8. So it'll be 0, 0, because it's all along there. It's going to be 0, 0, 2, 0, 0, 3, 0, 0, 4, 5, 6, 7, 8, and so forth. We can do a similar sort of thing along this direction here. If we were to count along these sets of planes here, that would be along the B direction. So that's the that would be 0, 0, 0. This would be 0, 1, 0, 0, 2, 0, 0, 0, 3, 0. Okay, so each of these reflections here is, on indexing, we're able to say that these are those particular reflections. Now, what does that mean for here? So the difference here is we've got the reciprocal lattice, we've got our points in here, but instead of, you can see that this point is just over here. So let's take that point, that is the 1 along A, so that is going to be 1. Nothing along B, and it's going to be 2 along C. Okay, so that's going to be 102 reflection. Okay, now you can see that placement of that thing is just over here. This is the reciprocal lattice point. Now what on earth's going on? Right, well, if we go back to our diagram over here, if, for example, I'm going to go have my 0 here, B is going to be into the direction of the board. We've got A and we've got C here. Okay, what that spot in that reciprocal lattice, we actually equate to what's happening in the unit cell. So this is now our direct lattice. This is what our crystal looks like. Okay, and therefore we've got what did I say? It was one along A. So what we'll do is we'll go along A, and then we'll just put a marker along A somewhere. Okay, to designate the 1. So remember, with the Miller indices, if we've got any integer number, we will have an integer number. It has to be. But if we've got any number, we're going to do 1 over that number, 1 over n. Okay, so for example, in this case, it would be 102. It would be 1 over 1, which is just 1. Okay, and we can go along the A direction and cross at 1. Now, I'm seeing you're a bit puzzled there, Banaz, so we'll look at number 2 then. So if it was the 102 reflection, let's forget about B. So we're looking at the 2. What's that? Where am I going to put my cross on this box here, on the unit cell? For a 2.
Is it just beside the C?
So you'll travel along the C. But whereabouts is it going to be? Okay, I've said that whatever integer number you have from your Miller index, it's 1 over that integer number. Okay, so our integer number is 2.
So 0.5.
So where is it going to be?
Middle.
1 over 2.
Middle.
So in the middle?
Yeah, okay, so it's just going to be at a half. Okay, so what we can then do is we can then get a ruler or a crystal impact box, and we can then draw that plane in our crystal. And remember, this is our direct space. Okay, so this is what our crystal looks like. We've just drawn a box. Our atoms are somewhere placed. I don't really know how we've come to this. I've forgotten what my train of thought is, but anyway, we're here. What was the original question?
Solving the basic problem. That was a while ago, to be fair.
That was, right, okay. So what we have on the crystal structure is we're getting a diffraction pattern. That's all Bragg's law. Okay, now what we have is a set of reflections along here that we need to work with. Okay, so you can imagine this is an infinite set, and so there's another set of reflections up here, 2. Okay, so this is the 102 set of reflections. Does that make sense?
Yes.
Okay, so they're just parallel, or they're meant to be parallel with one another. Okay. Now the question then is, yes, the phase problem. So if, for example, we have our benzene ring or cyclohexane ring in here, remember that what we've measured is some sort of intensity. It could be weak, it could be strong, but it's got somewhere. So say, for example, we have got our inversion center somewhere here, maybe, okay, in our system. Now, what's going to happen is that that's in our crystal. What we're then looking at is what is the electron density along this plane, these sets of planes. Obviously, there'll be a different this one and this one. So what we wanted to look at is how much electron density is there in this system. So you can see that you're getting some sort of electron density on that plane because there is an atom here, and some sort of electron density here because of that atom here. Now you know that if we've got our unit cell up here, okay, so we've got our repeating unit, we've got our long range order of our system, if I can draw, we've got our long range order. If you imagine this one here and this one here, they are a d-spacing away from each other. Okay, and another way of thinking about this is actually for us to have a proper diffraction. One way in which we can start to think about this is that over this d-spacing, there needs to be one wavelength. Okay, because they are going to be constructively interfering with one another. Okay, this is one way in which I can kind of picture this. Okay, so you can imagine you've got some sort of a wavelength of, you can put two wavelengths in here if you want, but this is just for the 100, we've got one, sorry, the 102 reflection, we've got our wavelength in here. Now what's going to happen is this atom here and this atom here have to be constructively interfering because they are long range order and the waves will be working together. If, however, you get an atom that sort of sits in here, in the middle between these planes, what's that going to do? That's going to be fully out of phase with each other, isn't it?
Yes.
If I was to have another atom in here, randomly, okay? So these things are interacting fully with one another. However, the relationship between this atom here and this atom here is deconstructive. Okay? If there was an atom here, it would be somewhere in between. Okay? So you can see here that if you only had atoms on this plane, everything would be constructively interfering. There would be no issue with the phase problem at all because they would all be in phase with one another. But as soon as you start having atoms off that plane, then you incrementally get worse and worse. And it means then the phases incrementally get worse and worse. And it's that relationship between this phase and this phase. We don't know what the phase difference is between those scattered waves are. Does that make sense? That's the way I think about it. Others may have other ideas. Okay, but that means that you're starting to see how you've separated out your Bragg. Your Bragg diffraction is just because it's crystalline and it's long range order. Okay, and that's fine. But then you need to think about now. What the Bragg, it is a crystalline substance. We're dealing with a crystalline substance. Now we need to actually think about, okay, where are those atoms within that unit cell? Okay, and that is the interesting part. That's where are the atoms and how much. And if you imagine that for this reflection here, you're getting an intensity X for another, for the, I don't know, what would this be, Banaz? Or Sadia? Sadia's been quiet too. What reflection would these be? So where am I cutting through the unit cell? Where's the plane cutting through? So remember, you've got a position A, B, position relating to A, position relating to B, and position relating to C.
C.
So where are you cutting A?
A and C?
So you're perpendicular to A at what value? How many unit cell lengths? Or fractions of unit cell lengths? What is that?
What is it, 100?
Yeah, okay, so it's going to be, you're cutting through 1 for A.
Uh-huh.
You're never ever cutting C, it's just parallel to C and it's parallel to B as well. So let's forget about that. So it's 0, 0, but remember, you've got 1 over 1, because you're cutting at 1, so it's this thing 1 over 1, which is equivalent to 1.
Yeah.
Okay. That makes sense? So remember, that's 1, we need to think about it as 1 over n. In this case, you're cutting n of 1, okay? If you were here, the n would equal 2. If you were here, n would equal 3. That makes sense? And therefore, if we drew lines here and here, that would be the 3, 0, 0. Okay, mark. Okay, but so there's this sort of balance between each of the different reflections. That kind of builds up a picture oh, this is a strong one, this is not, this isn't, and you're starting to see how that intensity may vary over each of those reflections, and then give you an answer as to where the unit cell is. Yeah?
Yeah.
Is that better, Julia, or is it worse? Have I just confused matters completely?
No, actually, it was better, more visual.
Sadie, you okay?
Yes, kind of. I still need to. I haven't read, so I still need to read and then. But yeah, I'm getting what you're saying.
Okay, so I think there are other school notes in the Oswald Drive if you want to have a look at them.
Okay.
They may be like a year out of thingy out of date, but they are there.
Okay, fine. Yeah. Thank you.
Okay, okay. So I guess that is that. So we've got some sort of ideas to how the structure is getting there. Okay, in terms of can we tell anything from the reciprocal lattice about our structure? Feel free to.
Molecules are from each other on atoms.
Pardon, sorry?
How far things are from each other. Okay.
Yeah. From the reciprocal lattice?
Yeah.
What things are you thinking are distance from one another?
So isn't the distance between the reflections in the reciprocal lattice the opposite of what the distance between, say, the asymmetric units is in real space?
Asymmetric unit?
Yep.
What's the asymmetric unit?
So the smallest repeating unit.
Okay. Does the asymmetric unit have to be contain full molecules?
No, it can be part of the molecule.
Okay, so it can be part of a molecule. So what's the thing that we're wanting? So if it can be part of a molecule, then we're not really able to repeat that because the part of the molecule might be have some sort of symmetry that will regenerate the other. We can't translate it. So is it the asymmetric unit you're wanting, or is it something else?
Something, no, it's something else. It's the
Sadia, White, or Banaz, what's the difference? What are you, from the reciprocal lattice? Julia's right, it's 1 over something, 1 over E value. Okay, so we'll go back again, we'll go back up here. Then what we've got here is our measuring tool. Okay, so what we're doing is we're looking here at 23.5-ish. Okay, and if you look over inside here with the unit cell tool, what is that? You're getting a unit cell length. Okay, so you're right in the sense that you can gain access to what the information is about the unit cell, but you can't really tell anything about the structure per se. You can't see where the atoms are, unless of course you're dealing with solids that have atoms on lattice points. Okay, so there's a big thing. I don't know whether you've been on Twitter, but what's his chops? What's his name? Oh, Christ. Name escapes me already.
Is it someone that goes by the initials AMG or something?
Yes, Mike Glazer. Right. So Mike Glazer is a huge, absolute Goliath in terms of crystallography. Okay, and he has a very big points. So what we're looking at here in our reciprocal lattice is a set of points. Okay, they are a set of reflections are a set of points. That can be deemed as a lattice. Okay, and a lattice is an array of points. Now, as soon as you get into putting in atoms together, okay, and putting in molecules and atoms, then they are no longer crystal lattice. Okay, there's no such thing as a crystal lattice. Okay, it's a crystal structure. Okay, this here can be deemed as a lattice because these are just points. There's no information. There's no molecules in here. Particularly, it's just an array of points. Whereas, once you start talking about molecules and the crystal structure, think of the crystal structure. Okay, so that's one thing about write-ups, about papers, about things like this. When you are writing it down, when you're writing your thesis or whatever, make sure you are talking about crystal structure, because it's very easy to get into starting talking about crystal lattice. Now the confusion arises, or the argument arises from certain elements of the community, in the sense that if you have minerals or very high symmetry materials, then the atoms can actually lie on the origin of the unit cell, and therefore you can start to say, well, it's just the lattice then. You know, and that's where those folks kind of come from, because those materials are so high symmetry, they're on those special positions on unit cells, and therefore you can say they're lattice points, essentially, and that's why they say it's a crystal lattice. Okay, so you can imagine that in here you've got your reciprocal lattice is 0, 0, 0, or whatever, but in your crystal structure, the atom will be at 0. And therefore it's just going to start to be an array of points or array of atoms, and therefore they say it's a lattice rather than a crystal structure. Okay. So it's useful to us. Okay, so the reciprocal lattice can tell us quite a lot. Okay, how are we going to use that practically? In society, how are you going to know whether it's worthwhile collecting something or not?
If they are in a row, like they are constructing. If they are in a row, then like if they are in between the lines, so which means like this, like we need to clean up the data.
Okay, yeah. So say for example, we've got a hole in a smush like this. Okay, that's okay. You're saying you want to clean it up. But say we've done all the cleaning. Say we've done all this stuff here, and you're getting this unit cell out here. Why is it interesting? How's just all you've done is taken the diffraction pattern. You've done pretty much nothing, yet it can be really useful to you in the science that you're doing. So why would it be? What would make you think, oh, this is worthwhile collecting, or this isn't worthwhile collecting?
Yes, there's a novelty factor, because we have the database, you can search against it, see whether something's already known or not.
Yeah. Okay. So, Sadia, for example, in your systems, you're looking at potentially new salt forms.
Yeah.
Okay. Are you interested in seeing your dihydrate again? Are you interested in seeing that, collecting a data set of the dihydrate? Or are you more interested in looking at new salt?
Like I will look through the unit cell parameters and compare it with the one which are in the systems, which are already known. So if it's like it's the same, so yeah, but if different, then we can say that it's like for it is something new.
Is that interesting?
Yeah.
Yeah. Okay. So you want, and this is, it comes to what's interesting to you. Okay, and what's interesting to the project? Okay, so I guess for yourself, Banaz, being a little bit newer, what is interesting? Is it the fact that something stayed the same, or is it the fact that you've got something new? Now, in Sadia's case, then you're looking at a new salt form. If you're trying to determine what the new crystal structure is, you do not want this unit cell to be the same as your original starting material. You want to see a new thing and therefore solve a structure. if, for example, you are doing a high pressure data set, Julia's been doing, where you just want the same phase all the time, then you want to make sure that is the same phase and you're going through that. Okay, so there's, just from taking the diffraction pattern, it tells you what you want to do and whether you want to collect or not. So if you saw the dihydrate, for example, Sadia, come up again, is that interesting? Well, it's novel enough, but you don't want to necessarily waste another 2 hours collecting data on the dihydrate, because there's no point in having a crystal structure.
Yes, yeah.
Okay. Whereas it may be useful for Banaz, for example, for your ambient pressure collection of one of your crystals, then you want to take a data collection. Once you've done it once, and that's it. You don't need to worry about it again. Okay. So it is useful. It tells you a little bit. Does it tell you anything? I mean, it tells you about phases. What other things are important that can help us when we're data collecting and maybe shorten data collection times? This is outside of a cell, for example. It's just what other interesting information is here for data collection, for example. Okay, so let's say as soon as we shine an X-ray on a crystal, is it diffracting? And where is it diffracting? Where is the crystal? Is it diffracting just in one direction where your camera is, or what's happening?
Well, that's diffracting to all three dimensions.
Depends on the collection strategy you go for.
Yeah. Okay. So you're right. So as soon as your crystal's illuminated, it's going right, and it's showing that diffraction pattern. Okay. Now there is a tool that I've downloaded to my other PC, not this one yet. Is that Len Barber diffraction tool, which is really helpful. It demonstrates what you're wanting, what we're seeing. Okay, so as soon as you shine your X-ray, Ben Len Barber. There we go. And he's got a piece of software that demonstrates as soon as you shine a light on it, it then illuminates and gives you your idea of things. Eval sphere, here it is. Let's go down. And I'll show you maybe later on. Okay, so it's illuminated all the time. So you've got a sphere of data, shining light, you've got a sphere of data that's being elastically scattered from the crystal. Now what, then we move our detector around, we move our crystal around, okay, to try and find all our reflections. The question is, do we need the entire data set? Do we need to do the entire sphere of data?
No.
Who said no?
Lots of shaking heads.
Okay. So you've got, it doesn't matter, right? So you don't need the whole sphere of data. Why is that?
Depends on the symmetry in the system.
Okay, depends on the symmetry of the system. Good. And what then? Okay, so in terms of symmetry, what's important?
So if you have, for example, a highly symmetrical system, you can get away with collecting just a fraction of that sphere, because then what you're getting is that data sort of you invert it, for example, or such, just to get your full sphere.
Okay, so what? So you're saying that you don't need to. You've got an inversion of it. So what you're saying is, if you transform a Miller index into another Miller index, then you don't need to collect that second one. Is that what you're saying? But if you've got HKL, you don't need to collect bar H bar K bar L for an inversion center, for example.
Yeah.
Yeah. Okay, so you've got that. So and there's various combinations of that. Okay, so if you've got a structure in P1 and you wanted to do the entire data set or not, okay, does that diffraction pattern have symmetry?
So it will have the inversion center, right? But that's not it.
Okay, so your diffraction pattern has inversion symmetry. So all diffraction patterns have, not all diffraction patterns, but we've got inversion symmetry to a degree. Yeah, essentially you've got a bar one. So whilst you can get away with just doing a hemisphere, then you only need to take half of your data set. Okay, but if it's a P1 or something, is it better to take that hemisphere or is it better to take the full thing?
You'd rather
What's
just
the
do.
advantage of it?
So if you take the full through, you'll have more data.
Yeah, why is that good? You just
Because,
said those reflections are the same, so what's the point?
but then you get higher intensity.
Intensity? Not that.
High intensity flat.
The higher intensity would only be related to the power of your X-ray source and or changing your atoms to be something more highly scattering.
I changed my answer. So isn't that related back to what you were mentioning at the start of the meeting, that if we have more data, say more reflections aligned, there you get sharper peaks with sharper points where the data is, and then when you get to solve your structure, it's much.
Okay, so that's the inherent property of the crystal. Okay, so it's got, once you've got the crystal, the sharpness is there. But if you're saying you're getting more data, okay, why is it important to have, I've got the term redundant data? The number of times you collect a reflection or something, that's the term redundancy or its equivalent. So why is it that important?
Because the more data you collect, the more confident you have that you have the correct model once you've solved it.
Yeah. So you've got so you have more data to help you. And what process do we have after integration? If you're going through the process of, if you go through Apex or whatever chrysalis, what's after your integration? What are we doing?
Reduction.
So that the integration is part of the reduction process. But that's what you do after your integration. You just name the things. You don't know what it is.
The one for X prep, isn't it?
Yeah, that's right.
Saint or Sarah?
No,
But I forgot the name on the
yes, that does. Right. Okay. It's scale. The scale button.
scale. Yeah, sorry.
Okay. Okay. So what are we doing with SADABs, Adia? You know?
I forgot because I haven't processed it recently.
No. Okay. No worries. So
Sorry.
then that's what we're doing there then. What are we doing in SADABs? No?
Refining it.
Not refining it. No. Or we're refining some parameters when we do that. Yes, but it's not refining as you'd expect for crystal structure.
It's the one and it's like the image. It goes like, and it's like 4 different graphs.
But what are we doing with SADABs? That's what it's called. Focusing on the abs part of it.
I forgot what the name of the values were, but it comes up with values and we see the trend. If it's
Do they ever get any ideas?
correction for the actual absorption.
Yeah, okay, so it's absorption correction. Okay, so what you're doing there is you're trying to find out how the absorption correction is working. Okay, now if we do that absorption correction, if you've got, and the way it does that is by looking at different reflections and equivalent reflections. Okay, so we'll look at the 1, 0, 0, or the bar 1, 0, 0, or we'll look at the 1, 2, 3, and the bar 1, bar 2, bar 3, or whatever symmetry equivalents there are. So at the very beginning of that scale function, it asks you what symmetry your crystal is. Okay, it will say bar 1, 2 over m, 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 and so forth. This Lowry symmetry. Okay, that's called the Lowry symmetry. That's the symmetry of your diffraction pattern. Okay, L-A-U-E. So that's the symmetry of your diffraction pattern. And what you're telling it is that actually we've got M, M, M symmetry. And therefore, within your data set, if any of your reflections are linked through that symmetry, they should be equivalent. Okay, they should have the same intensity. If there's variation there, then it starts to build up a model of, okay, why is that? Why is that one a little bit lower? Why is this reflection here lower than this one? How is this one lower than that one? And so forth. And by doing that, you can start to think about, okay, if I've looked at my system through this way, and then I've maybe looked at it through this way, and I start to build up a picture of what my crystal looks like, okay, and the shape and the size of the crystal. And so that's what the absorption process is like, okay, and that's what's happening there, and that's why you want to collect more data if you've got the opportunity to do so. If it's overnight or something, then you want to collect that redundant data. Doing a sphere rather than a hemisphere, whichever is useful. Okay, and that's why you want to fill in time with the diffractometer, especially with a new one. For those of you using it, you've got a lot of time in your hands. The intensity is good, and so you can collect a lot more data. If, for example, you've run out of time and it's finishing at 4 o'clock in the morning, just do a 360 degree phi scan at a particular random motor positions. Okay, that will give you extra data that you can collect. There's nothing wrong with it, it's just collecting more data, but you're using the machine, you're using time. There's no point in the machine time being wasted, okay, being stagnant overnight. Okay, so we're seeing here then, kind of going back to this, I guess, with the unit cell, you're sort of seeing some sort of symmetry here. So what's the symmetry here? Not been asked because this is your crystal. Sadia, what sort of symmetry do you think this might be? Or what crystal system do you think that is? Or do we need to go into crystal systems first?
Mono. Triclinic.
Okay, so why are you saying it's triclinic?
Mm-hmm.
I'm not saying it's wrong, or I'm not saying it's right, I'm just asking you why you think it's triclinic. Okay, for a triclinic system, what does the unit cell have to be?
Like all of the angles, they are not, like angles and lengths, they are not equal. Most of the systems, they are triclinic.
Yeah, okay, so for a triclinic system, the angles, the lengths don't necessarily need to equal anything, and they can. Okay, so you could have a triclinic system with 90, 90, 90. It could happen. Okay, however, it doesn't need to have any values. Okay, what does this? Okay, so at the moment it's looking triclinic. What system do you think it could move into, though?
Monoclinic. Actually, I don't know from the reduced data to see how we can. No idea. No.
If you look, so the let's look at the lengths here. Could these be anything?
Yeah, the two of the lengths, they are the similar, but one is.
So if two of the lengths are similar.
Yeah.
What else could that be then? What's that? Okay, it doesn't matter. We can come on to this. Okay, so if two of the lengths are similar, then it could be something like tetragonal, okay, or hexagonal or trigonal. Okay, that could possibly be the case.
Fine.
Okay, but then we need to think about what the angles are in that case. Okay, we've here got maybe two angles that are near enough 90 and one that's different. Okay, and if you've got two angles that are near 90 and one that's different, then you're into monoclinic straight away.
Mm-hmm.
Okay, so the monoclinic crystal systems. If we come up into the determined unit cell here, and Bravais, so these are your 14 Bravais lattices. Okay, and we'll come on to these next time, I guess. We've got monoclinic P, which is saying that it should be 90, 90, and then this 96 angle in the middle. Okay, and we transform that to be that value there. Okay. Now, one thing, so we can click on this button. Okay, we can go and do that and click on that button. But what I'm going to do is I'm going to cancel that for the moment, because I'm going to do something that kind of goes back to the problem Julia had, and I said I would demonstrate and go forward with. Okay, so what we have here is we've got a unit cell here that we're not quite sure of the orientation of it, and we don't think it's correct. And this is where we need to have a look at what our how we might transform that into something. Oops, let's refine that. Okay, so we've got a good refinement of our atom positions here. Now what we can do, and this wasn't the way that we suggested with Julia if it's within Apex, but say for example this wasn't quite what you wanted it to do and it wasn't doing what you wanted it to do. Okay, say for example, you want to transform these unit cell dimensions somehow. So you can see here that this is the result so far. What we've got is we're using a transformation matrix. Okay, and these are 3 by 3 matrices. Have you done much of this, Sadia?
No.
No? Okay, so we can maybe separately go through this at some stage.
Okay, fine.
Okay, what we can do is we've got our 3 by 3 matrix here. And essentially what we have, let's just ignore the angles here, is that we've got a 3 by 1 vector as well, okay? So 3 by 3, okay, so 3 rows and 3 columns. So remember Roman Catholic or Richard Cooper or something like that. Richard Cooper is the director of the Durham School. But if you want to think about Roman Catholic is the way in which we describe matrices. Okay, so it's rows, so it's three rows, and it's 3 columns. So that's why it's Roman Catholic. Okay, or any other RC that you care to know. I understand that there might be a situation where people are offended by using the word like this, but that's what we meant. Okay, so we've got our matrix here, 3 by 3. Now, if we've got a matrix that's 3 by 3, so if you write that down, if then your next vector is going just to be 1, 2, 3, okay, so that's going to be 3 rows and only 1 column. Let's just forget about the angles. Then you have a 3 by 1. Okay, and if you've written them side by side, what you should see is that the 2 middle numbers of the matrices are the same. Okay, so your matrix. So if we think about, let's just scroll on a screen. Scroll on a screen. Right, so we've got, oops. Where's that gone? No. Can you see this?
Yep.
Okay, so we've got a 3 by 3 matrix. And then we've got our unit cell, which is going to be a 3 by 1. Okay, so as I said before, RC, RC. Okay, rows, columns, rows, columns. What you'll see here is that these two things here are similar. Okay, they're the same number, and the output from this is going to be a 3 rows and a 1 column. Okay, so our result of our thing is going to be a 3 by 1. That makes sense? So after this transformation here, we should input a 3 by 1, which is our ABC. We do a transformation, and we will get a 3 by 1 out. Okay, so we're going from one unit cell to another unit cell. Okay, if, for example, we did a 3, if we did it in this way, like this way, are we able to do it?
No.
Are these numbers the same in the middle?
Mhm.
No? Okay, we can't do that. It's just not possible. We're not allowed to do it mathematically. Okay, so the way in which we approach this problem mathematically is we need to have it in this orientation. Okay? So what we're going to do is that we're going to start off with our 3 by 3 matrix. Okay? That's right on the left-hand side of our diagram. And we're going to multiply this by your vector here, okay, to create something else. Now what we need to do is we need to think about how are we wanting to orientate, what are we wanting to do to get into a monoclinic system. Okay, we want to change this so that we have got 22, say 6 and 23. That's what we're wanting to be our output. Okay, so at the moment we're 6, 22, 23, and we're wanting to get our answer, we want to be 22, 6, and 23. Okay, that's the two ends of our input and our input for this one here, and we've got this here, because what we're wanting to find out is, or use, or we want to try and manufacture some sort of 3 by 3 matrix to be able to do this. Okay? So the question I have to ask myself is, okay, what am I trying to do here? Okay, so if I look at this matrix, I want to move 6 into the second position, and I want to move my 22 into the first position. Yeah? And then 23 can just stay as it is. Yeah? Does that make sense?
Yep.
You okay, Sadia? Yeah?
Yeah, yeah.
Yeah? Okay, so that's what we want to do. So how do I go about doing this? Well, I'm going to use this matrix here. Okay, so in this first row here, that is going to impact, that's going to work, that's going to do something to this first position here.
Okay.
Okay, so this first row is going to do something to this position. So what I'm wanting to do here is I'm wanting to result of doing that. So I'm going to have to switch off my annotating. So in this system then, what I can do is I can just change these values to be whatever I fancy. Okay? So what I want to do is, let's go about and do, I'm going to put a 0 in there, I'm going to put a 1 in there, 0, okay? And then this one here, I'm going to say I want the second position, I want that to be number 1, I'm going to make that to be 0. Okay, and we'll leave in the bottom one. Okay, so what I've done there is I've tried to do that, and it's not going to help. Okay, so there are only certain transformations that you're allowed to do. Okay, and the reason for that is because you've got a right-handed rule. Okay, things have to be at right hand. Okay, A, B, and C. If I apply that, what's going to happen is that I'm going to transform that right-hand rule into a left hand. And that's not possible. Okay, that's not what we're wanting to do. So for us to be able to swap two positions, you can see that if I'm worried about swapping these two positions, this one's pointing up. If I swap them over, this one is now pointing down. Does that make sense? Okay, so I'm going to have to make one negative. Okay, so what I'll do is I'm just going to make one of these negative, and hopefully that will enable us to have that matrix. So I've done absolutely nothing. I've put in those points, and I've been able to transform my unit cell into the one that I want. Does that make sense?
Yeah. Yes.
I make this mistake all the time in terms of adding a -1 or not. Okay, I always do it, and it's just a trial and error. I mean, if I thought about it a bit more, then it would work, but I don't, so I just throw in numbers. Okay. Now the question you're probably asking yourself is, why have I chosen it to be looking like this? Why do I want 22, 6, and 23? Okay, if you look at the original setup in the top corner here, you can see that my a-axis here and my alpha are linked to one another, and my alpha is looking at 83. Okay, for a monoclinic system, that really should be beta. Okay, the odd one out should be the beta angle, and therefore to be able to do that, I'm moving my unit cell axis, the unique unit cell axis, which is the 6. I know it's the unique one because it's opposite the unique angle, and therefore I move that 6 to be in the center. That makes sense? So if you treat your alpha and your betas together, you use them always together, they're always together, so the length, so alpha will be with alpha, beta will be beta, and C will be with gamma, okay? And therefore I'm wanting to move my 6 angstrom axis so that it becomes the B axis, and by doing that, our beta angle will be beta. That makes sense? Or not quite, Savia? You're looking a little bit puzzled.
Yeah, I got some of it.
Okay, so we'll start, we can go through it again. Okay, so this is your starting unit cell up at the top corner here. Okay, so that's 6, 22, 23.
Yes, yeah.
Yeah, and we've got alpha, 83, 98, and 90, essentially. Okay? What we want to do is for monoclinic systems, we want the unique axis to be B, and the unique angle to be B.
Yeah.
So somehow we're needing to transform this and put that in the beta, in the B place.
Okay.
To move the 6, so it's in B.
Mm-hmm. Yeah.
Therefore, beta, the angle will be beta.
Okay, yeah.
And so that's the reason why we're doing it. We're using just the unit cell vectors, just the lengths, to do this. We don't worry about the angle too much.
Fine.
The angle just happens. Okay, so by doing that, we've been able to transform that into something that's a bit more reasonable.
Okay, yep.
Okay, and that looks a little bit more sensible. So if we click on OK to that, you'll see that down here it's now changed, it's moved. So this top bit's not changed, but this bit in here has changed. Okay, and I can click on and go through the process again, refine, and then if I accept that and go to gravity, it's 22, 6, 23. It's not done anything. It's you know, our input here, the top put is the same, or is it?
No, the angles.
19, no.
Okay, so one's 96 and one's 98,
Yeah.
83. Okay, but why are they equivalent? Well, as you can imagine, you've got a situation where you've got an angle of a 90-degree angle here.
Yeah.
Okay, and you've got 90-degree. Let's do this. I'll maybe draw this out instead. Essentially, no, I don't need to draw it at all. So what essentially what we can do is, if you think about, it's just so. Okay, so here are my lengths here. Okay, so this is going to be B up here, that's C, and that's A. Okay, so remember we've got 90-degree angles between B. So B and A, that's your gamma angle, so that's 90. Remember these relationships, A and B, and so that's the gamma angle. B and C, and that's going to be your alpha angle, so both of those are 90 degrees. And so it's this one in here that's going to be your beta. Okay, Now, if you think about this, if we think of the other way of doing it, this is going to be 83. All you're doing is you're choosing that way instead. Okay, so now you're choosing this way for your direction. You've got this angle here, so you're going to be 180 minus beta. Okay, so if you do that to that equation there, then you get into 83 transforms into 96. Okay, and that's what it is. Okay. Generally, we have positive angles, positive being greater than 90. Just convention. Okay, so the problem that Julia had, I think, rightly or not, there was an 11, 7 and 17 or something like that. That was the problem that we wanted to have, wanted to solve. Okay, so that's our vector, unit cell vector. We are now, what was it, 17?
11 and 7.
11 and 7. So that's what we wanted to have. That's what she got out of whatever I did. And she wanted to have this thing here. So what would the matrix be for that?
So
remember, Roman Catholic, we need a 3 by 3 and a 3 by 1. Okay, so we're able to do it. So that's why we're doing it this side and not the other side. Okay. So what are we going to do? So for this, if we think about it, we're wanting 17 here. So each of these places, and this is where matrix multiplication comes in, Sadia. Okay, so what we've got is we're going to have some value multiplied by 11 plus some value multiplied by 7 plus some value multiplied by 17. Okay, and that will give us our first digit here. Okay, so the values that we'll need to do here will be a 0. 0 times 11, 0.
0, yeah.
Plus 0 times 7. Plus 1 times 17.
Yeah.
We do that same thing for the 11. So what we're going to do here now? What's this row going to be? So something times 11 plus something times 7 plus something times 17.
So that row 0.
To get 11 here.
That should be 1.
Yeah.
0, 0.
Yeah. Super. Okay. Final one.
That should be.
Vanas, what's the final one going to be?
Sorry.
So we have something multiplied by 11, something multiplied by 7, something multiplied by 17 to get 7.
0, 1, 0.
Yeah. Right? In this case, it was a orthonomic form, so it doesn't really matter. You're just always doing this. So you don't need to worry about the beta angle. Okay, so that would have been the matrix that needs to be used to convert that through. I guess the last thing, we've got a minute left. Why are we doing this? Why do we want to make sure? So say for example you're wanting to redo a crystal structure. Okay, so say you wanted to redetermine a crystal structure. Why are we wanting to just get big data to publish? Why are we wanting to transform unit cells from 11, 7, I mean, if 11, 7, 17, it's still 11, 7, 17, it doesn't really matter, right? You'll still have a crystal structure. Why might you want to actually have it in the correct order or a specified unit cell?
So when we are doing the high pressure studies, like we need to make sure that like
Okay, so
This-
we're doing a study anyway. So, but why should you want to have it in a particular order?
Makes it more searchable and relatable. If you
So you may be convention, so you may be conforming to convention a little bit more, but that 1711.7's, that's nonsense, right? It normally goes from sort of low axis to high axis. So why might we want to do 1711.7 rather than
In my case, if I'm wanting to compare data that we've already collected or has already been collected with what we're collecting, if the unit cell is consistent, then I can do that direct comparison. Whereas if not, say, if I'm looking at a plane in my system, for one, it will have a set of HKLs that will be different for the other, so then I can't directly say, look at that plane and be looking at the same thing.
Yeah, so I mean, there's consistency in data sets. So in your case, you've got two sets of data, the SATR and the high pressure, and you're wanting to make sure that they're consistent with one another all across the board. Okay, and that's great. Why else might we want to have a look at that? Why might we want to stick to that? What other factor?
Is it when you're on OLEX, where the atoms are positioned as well?
Yeah, okay. And so why particularly?
Because you'd get different HKL values if it was in a different order.
Yeah, okay, so what's gonna, you're saying if the different HKL values, okay, so what's that gonna, you've got a model that has, so you've got your data that have got HKL values, and then your model, okay, so that's the thing that you've input, and they've got different HKL values. So if you simulated HKL values, so what will happen what happens when you refine that model with this data?
It'll not overlap. Not it'd be my MS.
It would be it's unrefinable. Okay, so what you're doing there is you've got a model. The atom positions are based on 1711.7. Okay, that's where the atomic positions, and your fractional coordinates are based on halfway along A, halfway along B, halfway along C, or whatever it might be. But then if you've got a crystal and your data are in a different order, then your atom positions and the scattering based on those model positions are just going to be completely wrong. Okay? Because your half no longer equates to a half, it's something else, it's a half in a different place. Okay, so it's to get consistency with previous data sets as well, so it's not just yours, but it's also if you're wanting to compare it with, I don't know, Ward et al, or whoever it is, then you want to make sure that you've got a consistent set with them. Is that a good refinement? That could be a brilliant refinement. Really low R factor, well-written paper, clear, concise, and you want to follow that, say, look, that's the one I want to relate to, rather than these nobodies, Oswald et al, have really been shysters and not done very well with things. I want to compare my data with a good set of quality data and a good description, and therefore you're linking yourself to that data set. Your nomenclature, your numbering scheme, for example, the C1, C2, C3, that's the same as the other one. Therefore, if they're talking about bond lengths, angles, hydrogen bonds, torsion, and so forth, they're exactly the same as yours going through, and therefore you've got that direct comparison. It makes life really easy. Okay, so it may not be the right thing, 1711.7, but actually I know that historically everybody's referred to that paper by Chris Frampton, whatever it is. That's a really important paper, and therefore everybody links to it, and therefore that's why we'd have that in 1711.
Yep.
Good. So I will finally just post in the chat. So this is the Len Barber software. So there are two things or three things. There's Xseed, which is a difficult program that does give you nice figures if you can figure it out. Particularly if you, Dave, for metal organic framework, they'll also void analysis and void pictures, so it's maybe worthwhile attempting to learn. What it outputs are Poveri images, so it's really quite, it's nice. But I've not spent the time to look at it. The second set is the Abel sphere, so that's this model here. This thing here, where you can start playing around with various aspects of this, and you can start to move your crystal into the beam, for example, and let's just cheat. And you can illuminate, you can switch on and off the radiation. It's not coming up for me, but I haven't, this is the first time I've used it, so it's something just to be wary of, but it can show you what the Abel sphere looks like. You can change it to be copper, chromium, and you can see what the Abel sphere is and diffraction sphere for your system. Once it illuminates, it should be giving you diffraction pattern. It should give you some sort of frames as well. But of course, it may be that my thing is not working particularly well. Computer, but I need to figure this out for lectures in about a month, so I better get on with it. But it's something to have a look at and play around with. Good. And then there's crystallography true type, so it's inversion simples and things like that. So P bar 1, annoyingly in scripts, or whatever, P bar 3, P bar 4, whatever. Yeah. Lots of stuff. Okay. I hope that was useful.
Yeah, it was.
Yeah, definitely.
Yeah.
And just on that note for learning, just to point out, there's a CCDC webinar tomorrow on using Mercury for looking at disorder and porous materials, and probably the void space calculator thing as well.
Oh.
If anybody's interested in that.
I did get a nudge, so yes, you can do that.
It's just, I think it's 4 PM tomorrow. I think you can still, it's just free to sign up. What's it called? Unlocking new insights by analysing disorder, voids, and porous materials. Maybe not as useful to other people in the group, but worth flagging.
Yeah, that's great.
Okay, thank you.
So what we can maybe go on to next time is, do you want to have a think about this? So there are different concepts that we've got. So the problem with crystallography is you can go off from different angles at all. You know, you need to know this, and it all kind of intertwined. So we've gone through a few concepts there about the Bravais lattices, about unit cells, about Miller indices, about crystal systems, without really talking about them much when we've gone through concepts and things like that. So it's a question of, are there any things that you're wanting to go over again, or need to maybe slow down and let's go through it? I have in my head a kind of progression into thinking about the crystal systems and going into a little bit more of what a space group is and symmetry and that sort of thing. That's what's in my head. But before we get there, it might be worthwhile, do we need to revisit some of the Miller indices or anything like that? Is that something that we collectively want to do, or is that something that most are quite happy with, but we can catch up individually with Miller indices and get that background? Obviously, you can do some background reading around the subject and familiarise yourself, but is there anything that we've touched on today that we might not come back to, but you would kind of want to think about? So have a think over the next day or two, but the next step is, I think, crystal systems and then symmetry.
Fine.
Yeah, but no, I don't know if there's any copies of this knocking around in CMAC or in the X-ray lab, but I think the Oxford primer on X-ray diffraction and crystallography is a reasonably decent starting point. Well, not starting point, but if you've got notes on from Durham, it's easy reading alongside to familiarise. I need to get myself a copy.
So there's another book by Andrew Bond, which is essentially, it's for pharmaceutical chemists. So depending on what you're wanting to do, whether you're wanting it or not, but it's essentially the Durham School, but for pharmaceutical chemistry. So he's basically taken the notes and made it into a textbook, essentially. So it's more relevant, or not relevant, but it's maybe more relevant for Banaz and you, Sadia, and Julia.
Okay.
Maybe not so much to you, but it's the same principles, it's just changing molecules.
Fine.
So Andrew Bond is the person who's done that. So.
There's a physical copy in the library, Sari and Banaz, if you want to.
Okay.
Oh, is that? Oh, that's good.
Yeah, because I got it in first year, and then I was like, oh, who's written this review on the cover? Someone called Iain Oswald?
Yeah. I don't get money.
Oh,
Good.
I couldn't find that.
I don't think so, anyway. Or maybe that's what that pint was. Anyway. Payment for services rent. Okay, so have a think about that, and let's see if we can go on to that next time.
Fine. Yeah.
Okay.
Thank you.
Right. Tomorrow I'm going to be here because the two boys are still off school, and my wife needs to go back to work. So I'll be here. Friday I'm going to hopefully, without disease, be through in Glasgow. If not, I will let you know.
Okay.
So Sadia and Julia, we can just do it online.
Okay. Yeah.
And Banaz, I don't know if we've got a meeting. I haven't scheduled a meeting. Let's schedule a meeting, or if you want to shove something in tomorrow, and we can get that sorted.
Okay.
Okay.
Thank you. See you.
Bye for now.
Yes, guys. See you later.
Bye.